Hello guys, so welcome back to our last part for chapter 1, forces and motion 2. So for today we are going to talk about elasticity. So I hope that you are still okay in this chapter from resultant force, resolution of force, forces and equilibrium. Okay, these three topics are very important because they are kindly related to each other. So make sure you know how to find a resultant force, how you to do the resolution of forces, the forces and equilibrium for you to answer the question, especially in problem solving. I know your challenge is you are mathematics is hard for you, but I want to tell you that actually it's not hard as long as you practice it, you can do it. All right, so for today, we're going to talk about elasticity. Now, before we go on, what is about elasticity? First of all, we have to know what is elasticity. Elasticity. So, you know that there are objects in our daily life which has this kind of situation when you stretch it, you compress it, it will go back to your original shape or size, right? For example, sponge, spring. Okay, when you just return it back to the original situation, it will return to its original state. So what is elasticity? Elasticity is the property of the material that enables an object to return to its original shape and size after the force applied on it is removed. Now here, when you write a definition, please make sure you have all the key terms that needed. What is the key term? The property of the material that enables an object to return to its original shape and size after the force applied on it is removed. Okay, so these are the few words: removed, force applied, removed, return to its original shape and size. Okay, so please remember that. So let's say girls, we have rubber band, right? So normally we are going to tie our hair with rubber band. So rubber band, we have elasticity, property and characteristics there. But do you realize or not, after certain time you use the rubber band will not no longer return back to its original length. Why? Because it has exceed the elastic limits. Now, what is elastic limits? Elastic limits is a certain limits when you extended it at a certain point, it still follow the law. But after you extended it in until one length, it will no longer go back to its original shape, means that that point is the final limits of that elasticity. Okay, now when I talk about law, here's another law that you have to know. In chapter 2, form 5, you learn what one law. But when in form 1 and form 4, you learn about three laws, which is Newton's first law, second law, and third law. Okay, so that are the three laws that you learn when you are in form 4. So today, I'm going to introduce you to Hooke's law. Now, for Hooke's law, you are going to relate it to graph. So here, this is the graph of x against f. I'm going to explain to you what is x and what is f. Now let's go on first. Now, what is Hooke's law? Hooke's law said the extension of a spring is directly proportional to the force applied on the spring provided the elastic limit of the spring is not exceeded. Now, here are the keywords: extension of the spring, directly proportional, force applied on the spring, given that elastic limit of the spring is not exceeded. So you have to remember, like I said just now, everything with elasticity property will have elastic limits. That's the limit. Means that initially until this point, they are still following Hooke's law. Now, if you look at this graph, you know that the graph that starts from 0, it means directly proportional, right? The graph that starts from 0 means that it is directly proportional. So from here, this graph shows that x is directly proportional to f. But until this point, if let's say when a graph exceeds the elastic limits, you will have a curve at behind that. So that is what happened to if let's say the spring or the object exceeded the elastic limits. Okay, now, so how do I memorize this Hooke's law? I know if you want to memorize the whole statements, you feel tired and you feel like very redundant to memorize the definition, but let me teach you. Okay, how I remember this. Okay, how I remember the formula. Sorry, how I remember the definition. Okay, I remember it like this. I'm going to use this one. I always remember my definition by using the formula style. So x means extension of the spring. What is extension of the spring? Extension of the spring means that, okay, now I just give you one situation. You know spring, right? Before you hook on it, it will have length. So that is the original length before you hook on it. When you hook something on it or hook an object on it, it will be extending it. So when it extends, the extended length minus the original length, that extension is the extension of the spring. Okay, I repeat again. Original length of the spring you hook something on it, and then it will become extended, right? So the extended length minus the original length is the extension of the spring. Okay, so that's why we present it as X. So X is directly proportional to F. Now, mathematically, you can write F directly proportional to X. But if let's say during the exam, I do not encourage you to write Hooke's law is F directly proportional to X, because in words, it's actually extension of the spring is directly proportional to the force applied. Okay, but mathematically, F directly proportional to X is accepted. Okay, so in mathematics, okay, now because F directly proportional to X, then you have F is equal to Kx. Now there's a benefits why you have to put it F directly proportional to X, because it depends on the graph. Okay, sometimes graphs can be F here and X here. Okay, so what is F? F is applied force, X is the extension of the spring, and K is the spring constant. So F is equal to Kx is the formula of Hooke's law. Now let's say in class, I'm asking you, what is Hooke's law? Let's say you don't want to mention the whole segments of the definition. Extension of the spring is directly proportional to the force applied on the spring, provided the elastic limit of the spring is not exceeded. When I ask you in class, what is Hooke's law? You can say F is equal to Kx. So I know what you know. Okay, because orally, it's okay for you to answer that way, but in exam, please make sure you memorize the whole definition. It is better if you write in words, because sometimes we do not know what is the marking scheme needed. Okay, so I move on. So like I said, when it related to graph, you have to analyze graph. Now, Hooke's law, we will have one experiment we are going to conduct in one of the class that we are going to do in school. So, okay, before you do the experiment, I need you to know how to analyze the graph, because in that experiment, you need to plot the graph and also you need to analyze the graph. Okay, now physics and maths slightly different. Maths, you can just need to do. Maths, you just need to calculate, you just need to plot the graph. You are not going to interpret what do I mean by the gradient, what do I mean by the area under the graph. No. But in the physics, yes, you have. Okay, now I'm going to explain here. So if you look at this graph, this is actually a F against X graph. F against X graph. So just now we are looking at X against F graph, right? So now I'm going to tell you about F against X graph. So what do you know just now? Hooke's law is F is equal to Kx. To find the spring constant, K is equal to F over X. How do I get this? I bring the X to the other side, I get F over X. Am I right? And then based on the graph, if you look at this graph, I have to find a gradient, right? How do I find a gradient? The gradient is y divided by x. Y-axis divided by x-axis. So I have f over x. So my gradient is f over x. So when I combine them together, I know that spring constant is equal to the gradient of the graph when f against x. Now, let's say your graph is x against f, then the gradient do not represent the spring constant directly. You have to inverse the gradient for you to get the spring constant. Now, I'm going to explain further when I'm in class, okay? Remember to ask me. If you don't ask me, I will assume that you understand it. Okay, let's move on. So beside understanding how the gradient, you have to understand what is the purpose of area under the graph. Okay, here, I'm going to introduce to you elastic potential energy. Now, before I move in with elastic potential energy, I want to ask you one question. You have to find the answer, and I need you to answer me in class. What is you learn about energy and work done when you were in Form 3. You learn about energy and work done when you were in Form 3. So, what is the relationship between potential energy, gravitational potential energy, kinetic energy, and work done? You have to tell me in the class. Okay, go back, study it, find the answer. Okay, all right, move on. So in this diagram, in these pictures here, you can see here, elastic potential energy is equals to the work done to stretch the spring. Okay, so the formula is equal to average force multiplied with extension of the spring. So what is average of the spring? Average force. Last year, we learned about average velocity, right? So to find average velocity is initial velocity plus final velocity divided by 2. That was what you learned last year. So this year, talk about average force means that initial force, which is before you exerted the force, plus the final force after the extension divided by 2, and then multiply with the extension x. So I have 1 over 2 multiplied with fx. This is the formula for elastic potential energy. Then, based on the graph, to find a graph area in the graph, you can see that this triangle, green triangle, is actually a right angle triangle. How to find a triangle? This is right angle triangle. To find a triangle, area of the triangle is 1 over 2 height multiplied with the length, right? This is what you have. So The height is F multiplied with the length X. So that's why half multiply F multiply X, I get half Fx. So how do you relate them together? Now I just quote down whatever that I have just in the previous slide and I put it together. So when I put it together, you have this. Elastic potential energy is actually equal to the area under the graph F against X. So for the potential energy is equal to half Fx. So Hooke's law, what Hooke's law said? Hooke's law is F is equal to Kx. So I'm going to replace this F with Kx. So I'm substituting the Kx into the F. I get my potential energy is equal to half Kx multiplied with X. Then I'll get half Kx squared. So you have two formulas where you can find the elastic potential energy, which is half Fx and half Kx squared. Okay, it depends on how you use it. All right, now, so beside understanding about that, the area under the graph, how to find the elastic potential energy, how to get the gradient, okay, and then what is that? What does the gradient represent? You have to know about characteristics and also what are the factors affecting the value of spring constant. Now, what do I mean by spring constant? Now, spring constant is like this. There's a value for spring constant. When your spring constant is high, normally the extension will be short. Means that it's like this. If let's say your spring constant is high in value, then it is harder to extend. But when your spring constant is lower in value, then the extension is longer. Okay, I repeat again. So it's like this. If I have two types of spring, so type A, this spring is with a high extension, a high spring constant. This one will have a low spring constant. So when I hook things on, both same mass, then what happens is the one with the higher spring constant will extend a little only. But then the one with a smaller spring constant will extend further. So that is the difference here, spring constant. Okay. All right, now, so there are four factors affecting the spring constant, which is material of the spring, length of spring, diameter of spring, and thickness of wire. Okay, I'm going into one by one, but I will be focusing more on length of spring, diameter of spring, and thickness of the spring wire because these three factors involve physical quantity. What is physical quantity? Physical quantity is the quantity that can be measured, measurable quantity. Okay, now material of the quantity, material of spring, normally we cannot measure it except if you tell me what is the density of the material used. Okay, but then normally we are not going to talk about the density here. Okay, now, so the factors that changing is the different material. For example, the spring made out of copper, the spring made out of steel, the spring that is made up of nichrome. So these are what we call different materials. It changes according to the type of the material, okay? So let's go on length of the spring. Now, you have two types of spring. One is shorter, one is longer spring. So normally, shorter spring, when you hook on the things, the extension is actually lower compared to the one with the longer spring. The longer spring, when you put on it, it will be extending longer. So that's why the shorter spring will have a higher spring constant, and then the longer spring will have a lower spring constant. Now, how about the diameter of the spring? What do I mean by diameter of the spring is the diameter like this. Okay, the diameter like this. Now, the smaller diameter means it's smaller. The bigger diameter means your spring is bigger like this. Okay, bigger diameter. So your smaller diameter will normally have a higher spring constant compared to a larger diameter, which has a lower spring constant. What do I mean here? So means that if I have a larger spring, okay, larger diameter of the spring, when I hook on something, the extension is actually longer. So that's why the spring constant is lower. Okay, now how about the thickness of the spring wire? Thickness of the spring wire means the thickness of the wire. Okay, the wire is not the diameter. Please don't mess up. The diameter is the spring diameter, but the wire is actually the things that the wire itself before it is being coiled up. Okay, so the wire with a larger diameter, this is very obvious. The wire with a larger diameter will have a higher spring constant. It is harder to compress. For example, in motorcycle, if you observe at the side of the motorcycle behind there, there's a spring there. That spring normally with a very thick wire there. Okay, so wire with smaller diameter will have a lower spring constant. All right, we will discuss more in class if let's say you don't understand. Okay, now next one, we go on. So beside understanding on factors, okay, just now we have how to find a gradient, we have how to find the elastic potential energy, and then after that, understanding the spring constant, factors affecting the value of spring constant. Now we are going to problem solving. Now, using all the formula previously, for example, half kx squared, half fx, f is equal to kx is very important in problem solving. Another situation is when we give you arrangement of the springs in different type, which is in series and also in parallel. The one in series means that it is arranged in this style. And then the one in parallel means that you are going to arrange it side by side. So what do we have here? So let's say if I hook this one, the one in series, here I hook it 5 Newton. What happened to the tension of the spring? Means that when I hook 5 Newton here, this spring will experience 5 Newton of force. And then this one will also experience 5 Newton of the force. Okay, so means this is what it means by this. Now, another one, if let's say for parallel, if I hook a 5 Newton here, 5 Newton of force here, so what happened is both of the spring will be sharing the weight. They are going to sharing the weight. So when they share the weight, means that 5 Newton is going to be divided by 2, and then you get 2.5 for each spring. So that is what we mean by that. Okay. Now, the questions tend to be like this. Normally, we will tell you, okay, originally first, before I arrange it into series or before I arrange it into parallel, I'm going to tell you what is the extension and what is the tension and extension of that spring if I'm using only one type of the spring. For example, okay, I give you one spring. So that spring, I hook 5 Newton. Okay. Then after I hook 5 Newton, that spring will be experiencing 5 Newton of the tension. And on the same time, when I hook it on, this spring will experience 3 millimeter extension, for example, 3 millimeter. And then after that, I give you another spring, and then I tell you that this spring have to be arranged in series. So when it is arranged in series, you have to understand that the spring on top will experience 5 Newton of the force and extension 3 millimeter. Okay, and then the spring below also will be experiencing 5 Newton and extension 3 millimeter. So that is what we have in series. But in parallel, because that one, they are doing it side by side, so they are going to share the workload. So when they are going to share the workload, that's why it is divided by 2. But it depends on how many springs you have. If let's say you have 3 springs here, then you divide it into 3. If you have 4 springs, you divide it into 4. As long as it is in parallel, then you divide. If let's say it is in series, you just take it directly. Okay, now, next one. If let's say I want to find it for the whole system. Now, this is the whole system. Okay, so my force, I will be, the force here, okay, for the spring is 5 Newton. This one will also be 5 Newton, but the one that is going to change is the extension of the spring. So the whole system here will be experiencing 2x extension, means that this extension plus this extension. Okay, all right, now, so for parallel, there's not much different because the extension here, okay, is the same. So if let's say this one experiencing 3 millimeter, this one also 3 millimeter, so the whole system is only experiencing 3 millimeter of the extension. Okay, now I'm going into the example. We see how. So you see here, okay, I'm going to this example. All right, let's look into the first question. A spring with original length 50 millimeter. 50 millimeter is the original length, extends by 6 millimeter when stretched by a force of 12 Newton. Calculate the spring constant of the spring. Now, this is very easy because the question asks you to find spring constant only. Before you go on, you just type down what is the information that is given to you. I have my force 12 Newton. I have my extension 6 millimeter. Then what's next? By using Hooke's law, F is equal to Kx, I can find my K. K is equal to F over X. Okay, because you bring the X to the other side and then divide. Next one, substitute the value, and then you get 12 divided by 6, and I have 2 Newton per millimeter. Remember to write the unit. The unit is very, very important. If you forgot to write the unit, we are going to penalty you. Okay, so how do you write it? Actually, how do you find the unit? It's just mathematics. Newton divided by millimeter. Newton divided by millimeter is Newton per millimeter. That's it. Okay, easy, right? Now I move on. Okay, now let's see another question. Now I'm giving you 3 arrangements. I'm using the same type of the spring that was given in question A just now. Okay, the question. So I'm going to arrange them in P and Q. This is in series. So like I told you in the concept just now, because the spring is experiencing 6 millimeter extension, right? So P is 6 millimeter, and then Q is also 6 millimeter. I'm sorry, because the question is asking about the tension on each spring, right? So the tension is easy. The force, because I'm hanging 12 Newton here, so P will be experiencing 12 Newton, Q will also be experiencing 12 Newton. So that's it. And then here, R and S, because they are sharing the same load, so that's why R 12 Newton divided by 2, so I get 6 Newton and 6 Newton. Easy, right? Okay, now, only the one with challenge is this one. Okay, in here, you have to understand how to look into the system. First thing is, we are going to divide them into two parts, the upper part and the lower part. So both upper part and lower part will experience the same tension, which is 12 Newton. So means that TUV 12 Newton, W 12 Newton. So to find W is still easy. W is equal to 12 Newton lah. Then next one, TUV divided by 3. So you have 4 Newton respectively. Okay, then move on. So to find the extension of spring, I accidentally answered the question just now. So I hope that you get the answer. So P and Q, because one spring experiencing 6 millimeter extension. So P 6 millimeter, Q 6 millimeter. And then R and S, like I said, they are sharing the same load. So divided by 2. So that's why I have 3 millimeter and 3 millimeter. Then move on. Okay, now this one. That's the challenge. So because upper and lower will be sharing the same extension, right? Okay, so that's why they are sharing 6 millimeter above and 6 millimeter below. So this W will become 6 millimeter. How about TUV? Divided by 3. So I get 2 millimeter each. All right, easy, right? So move on. How about the total extension of the system? I'm talking about total extension of the system. So P6, right? Q also 6. So you just plus 6 plus 6 equals to 12. Sorry, 6 plus 6 equals to 12 millimeter. Okay, how about R and S? R and S, they are on the same plane right there, on the same plane. So they are only experiencing 3 millimeter. Okay, divided by 2, right? Okay, all right, then last one. Okay, so how do you see this? For W, 6, right? For TUV, 2. So the total, 6 plus 2 equals to 8 millimeter. So that's how it is. All right, I hope that you get that. If let's say you really don't understand, you can just ask me in class. I'm going to already explain it again. Now here, last one. The total length of the arrangement of the spring. Total length means that you have to include the original length. So I know that P and Q is 12 Newton at 12 Newton, 12 millimeter extension plus 50-50. So I get my arrangement 1. Arrangement A is 550 plus 50 plus 12, 112 millimeter. And then R and S, I have only one plan. So easy. It's only 50 plus 3 is 53 millimeter. Okay, then last one. Okay, one by one. So we are going to look into one by one. First thing is we are going to look at TUV. You remember, right? The extension is 2 millimeter. The original length is 50. So that's why 50 plus 2. Then next one, I have 6 millimeter extension, right? So 50 plus 6. Then total up, I have 108 millimeter. Okay, so I hope that you understand what I'm saying here. Okay, I hope that you understand. Try to figure out and understand this topic because Hooke's law is very important. Okay, so that's all for the class. Thank you, class. See you again next time. Bye.